You have heard the question before, where is everybody? It sounds like an astronomy question, and for 60 years it has been filed as one. It is not. Tonight that question turns around and points at you, and by the end, you will not be able to turn it back. Start with the part that rarely gets said plainly. This galaxy holds roughly 200 billion stars, and has been running for about 13 billion years. If one species anywhere in it had begun spreading at the speed our own probes already move, they would have touched every system here before the first dinosaur drew breath. No exotic physics required. Chemical rockets and patience are enough. That arithmetic has been checked by people who badly wanted an error in it, and the error has not shown up. So the sky should be crowded. Why is it not? That gap has a name, the Fermi Paradox, and it has produced more serious proposals than almost any question in modern science. Now the part that should bother you. Out of all those proposals, you would expect at least one to be good news. One outcome where we look up, work out what happened, and exhale. Does such an outcome exist? Follow each road to its end rather than stopping comfortably halfway, and the answer appears to be no. Everyone arrives somewhere you would rather not stand. Not one safe explanation, not one. Tonight we walk down all of them. That we never really searched. That a signal arrives and nobody knows who picks up. That we're alone, and why alone is likely worse than hunted. That we came too early for a universe that was not ready. That growth itself is what ends civilizations, which would put the filter ahead of us rather than behind. That they matured and went where we cannot follow. That they are close, holding a silence that will not hold. 8 doors. We open everyone and stand there long enough to see what waits on the other side. Then something shifts. Each road stops being about them. Each one turns out to be asking us the same question in a different accent. Not, are you alone? Something narrower, with a deadline attached. Can you last? You will probably notice it before it gets said out loud. So we start where this started. A small room in West Virginia. 10 people. A chalkboard. And an equation misread almost every day since. The room was small and nobody expected it to matter. November 1961. Greenbank, West Virginia. A radio observatory sited there because the mountains blocked stray transmissions. 10 people were there. Among them a chemist, Melvin Calvin, who learned during the meeting that he had won the Nobel Prize. The organizer was a radio astronomer, Frank Drake, and his problem was scheduling, not science. He needed an agenda. 3 days of talk about whether anyone else was out there, with no obvious order to the topics. So what does a man do with that? He worked backwards from the thing they wanted to know and listed every quantity that would have to be pinned down first. That list became 7 terms, written left to right and multiplied together. It has been called the Drake equation ever since, and textbooks present it as a formula for estimating how many communicating civilizations share this galaxy. That description is wrong, and Drake spent decades saying so. It was never built to produce a number. It was built to break one impossible question into 7 smaller ones that could be argued separately. An agenda. A way of organizing what we did not know, so that 11 people in a room could disagree productively instead of in circles. Something happens when ignorance gets written as an equation, though. It stops looking like ignorance. Multiplication signs carry authority. Put unknowns in a row with operators between them, and the thing takes on the posture of a calculation, and a calculation feels like it is heading somewhere. So people plugged in numbers. Optimists produced millions of civilizations. Pessimists produced fewer than one. Both pointed at the same 7 terms and walked away. Certain. How is that possible? That should have been the warning. When an equation returns whatever you feed it, it is not answering you. It is reflecting you. And here is what almost nobody notices about that chalkboard. The terms are not equal. Some have since been measured with real instruments and real data. Others have never been measured at all, not once, and no current experiment could measure them. Which ones fall into which group? That division turns out to matter more than any number ever produced from the equation. Because when you sort the 7 terms by how much we actually know, a pattern appears in the gaps, and the pattern is not encouraging. Look at the 7 terms the way Drake sorted them. Because the sorting is where this turns uncomfortable. The first 3 describe hardware. How fast this galaxy builds stars, what fraction of them hold planets, and how many of those planets sit where liquid water survives. 60 years ago, all 3 were guesses. They are not anymore. The Kepler telescope ran from 2009 to 2018, staring at one patch of sky holding some 150,000 stars, watching for the faint dimming as a planet crosses. It found thousands, and the conclusion was that planets are not rare accidents, but standard equipment. Most stars appear to have them, and a meaningful fraction sit in the temperate band where water could stay liquid. So the first 3 came back generous. Hardware is abundant, and that was supposed to be good news. Now the other 4. What fraction of habitable worlds actually start life? What fraction of living worlds produce intelligence? What fraction of intelligent species build something that broadcasts? And how long such a species lasts once it does? How many measurements do we have for those 4? 1. Always the same one. This planet, this species, this century. A sample of 1 tells you something is possible. It tells you nothing about how often it happens. The arithmetic then does something cruel. Multiply the first 3 and you get a comfortably large number. Then multiply by 4 fractions that could each sit anywhere between 1 and 1 in a billion. What does that do to the result? The answer stops depending on the terms we measured. It depends almost entirely on the terms we cannot touch. 60 years of observation, thousands of confirmed worlds, and the equation is arguably no closer to an answer than on that chalkboard. Worse, look at the last term. Not a fraction, but a duration. How long does a communicating civilization stay communicating? Every optimistic estimate likely depends on assuming that number is large. Nobody has evidence that it is. We are the only civilization available for measurement, and the measurement is not finished. You are living inside the variable. The one quantity the calculation rests on is being set right now, by us, and nobody knows which way it settles. So if the equation cannot answer this, what about simply listening? 6 decades of searching ought to have covered enough ground to mean something. 3 astronomers asked exactly that in 2018. Jason Wright, Shubham Kanodia, and Emily Lubar at Penn State did something oddly rare. Instead of proposing a new search, they measured the old ones. They added up every published radio search since 1960 and compared the total against the volume of possibilities a signal could hide in. To do that, you have to define the space properly, and it has more dimensions than you would expect. A signal has a position on the sky, a frequency, a bandwidth, a polarization. It has a repetition rate, since it might appear once an hour or once a decade, and a modulation. And it has a strength, which sets how sensitive you must be to catch it at all. 8 dimensions. Miss on anyone and the signal passes through your instrument as nothing. So how much of that space has actually been examined? 2 teams have answered that, and both answers should end most casual talk about cosmic silence. In 2010, the SETI astronomer Jill Tarter put the searched fraction at 1 drinking glass, drawn from all of Earth's oceans. Wright and colleagues rebuilt the haystack differently and published in the Astronomical Journal. Their figure came out larger. A hot tub. Sit with that for a second. Against every ocean on this planet, a hot tub is indistinguishable from nothing. If you scooped 1 tub out of the Pacific and found no fish in it, would you announce that the ocean is empty? Nobody would take you seriously. Yet the phrase, "the great silence," gets used constantly, in headlines and in serious papers, as though it describes a result. It does not describe a finding. It describes the inside of a hot tub. There is a further problem stacked on top. Most of that searching was not aimed at the whole sky. It was pointed at selected nearby stars, chosen because they looked promising to us, for runs measured in hours. If a transmitter on one of those stars was switched off during the hours we listened, it registers identically to one that never existed. And the famous exception shows the shape of the problem. In 1977, a telescope in Ohio recorded a strong narrowband burst lasting 72 seconds. It has never repeated. We were pointed the right way at the right frequency for 72 seconds out of 60 years. So the silence you have been told about might not exist yet, which raises a harder question. What happens on the day it breaks? You might reasonably push back here. We have enormous telescopes, instruments that detect a single planet tugging on its star, instruments that read the chemistry of an atmosphere hundreds of light years off. Would something that sensitive not notice a civilization? The objection is fair. It fails for a reason that has nothing to do with sensitivity. A radio telescope does not watch the sky. It stares at one small patch, the way you would look through a drinking straw. The greenbank dish is among the largest steerable instruments on the planet. At typical search frequencies, its beam covers a fraction of the full moon. To sweep the entire sky at that resolution, one patch at a time, would take longer than the searches have been running. So every search makes a bet. Choose a few thousand nearby stars, look at each for a few hours, move on. Reasonable. It is also a bet that whatever is out there transmits continuously toward us in the narrow band we tuned to during the exact hours we were pointed at it. Now flip it around, because the bet becomes clearer when you are the target. Imagine you are on a planet 50 light years away, running exactly this search, and Earth is on your list. You get 3 hours. What are the odds those 3 hours land during a transmission? Here is the harder part. We are not transmitting. Not deliberately, not continuously, not in any direction that matters. There is a persistent belief that our television and radio broadcasts form an expanding bubble of noise, announcing us to the neighborhood. It is a lovely image, and the physics does not appear to support it. Broadcast signals spread in every direction and weaken with the square of distance. By the time our strongest analog transmissions reach even the nearest star, they are likely far below the background hiss of the galaxy itself. Any receiver there would need a collecting area larger than a continent to pull them out. So, are the instruments the limitation? Probably not. The strategy is, 60 years of searching has been 60 years of glancing, and the glancing was aimed at the wrong assumption. But that raises something worse than a methodological complaint. If our own noise is effectively undetectable, then what exactly would an alien astronomer see when they turned their equipment toward this solar system? Run the experiment properly. Put yourself 50 light years out, on a planet with better instruments than ours, and point them at this solar system. What actually reaches you? Not television, not radio drama. Those spread out in every direction and fade with the square of distance, which means they likely arrive weaker than the natural static of the galaxy. To pull them back out, you would need a collecting dish measured in hundreds of kilometers. What does reach you is much narrower and much rarer. Planetary radar, the kind used to bounce a beam off an asteroid and map its shape. Those beams are tight and powerful, and for the seconds they are running, Earth becomes one of the brightest radio objects in this part of the galaxy. Military early warning radar does something similar, sweeping the horizon continuously with far more power than any broadcast tower. So we are detectable, occasionally, in one direction at a time, for as long as the transmitter happens to be aimed at you. Now, the timing problem. In November 1974, the Arecibo dish in Puerto Rico transmitted a deliberate message toward a star cluster 25,000 light years away. It ran for under 3 minutes. It has never been repeated. If your civilization happened to be listening at that cluster during those 3 minutes, and happened to be listening in that exact band, you heard us. Otherwise, nothing. And Arecibo itself is gone. The cables failed and the platform came down in December 2020. The single most powerful radar transmitter humanity ever built is a field of wreckage in the Puerto Rican hills. Here is what that means when you flip it back around. If an alien astronomer had been watching this system for the past century, their record of us would be a handful of unexplained flashes with decades of silence in between. Would they file that as a civilization, or as noise? They would perhaps do what we do. Note the anomaly, fail to reproduce it, and move on to a target that looks more promising, which leaves one uncomfortable symmetry. We have been treating our own silence as an accident of technology, and their silence as evidence about the universe. Those two positions may not both survive. And the situation is about to get considerably worse, because the century in which Earth was loud is already ending. Think about how much noise your own house leaks compared with 20 years ago. The answer is almost none, and the reason is not caution. It is efficiency. Analog. Television broadcasting is gone across most of the developed world. The United States shut it down in 2009. Britain finished in 2012. Those transmitters pushed huge power into the open air in all directions, because that was the only way to reach a rooftop aerial. What replaced them sends the same content down fiber optic cable, or from satellites aimed straight at the ground, or through mobile networks using a fraction of the power. Every one of those replacements is quieter, and not by design, by economics. There is a rule hiding in that, and it may be the most important thing in this entire subject. Broadcasting in all directions is wasteful, because you are paying to flood the empty sky in order to reach one receiver on a hillside. Any engineering culture that lasts long enough will likely notice that waste and remove it. Directed beams replace omnidirectional towers, compression replaces raw bandwidth, and low power replaces high. Does any of that sound like a choice? It is not. It is arithmetic on a balance sheet. So what does an advanced civilization sound like? Increasingly, like nothing at all. Then look at what modern signals look like even when you do catch them. Digital transmission uses compression and spread spectrum techniques that deliberately make the output resemble random noise, because noise-like signals pack more information into less space. A sufficiently efficient message is arguably indistinguishable from static unless you already hold the key. Now, put a boundary around the loud period. Earth began leaking meaningful radio around the 1930s. It is going quiet in the 2020s, roughly a century. Set against a galaxy 13 billion years old, a century is not a phase, but a flicker. If that pattern holds generally, then every technological species emits a brief burst of detectable noise on the way to becoming permanently quiet. The window is probably not a stage anyone lingers in, but something you pass through on the way somewhere else. So what would a galaxy full of advanced civilizations actually look like from here? Exactly like this. Empty. And that possibility does something to 60 years of searching that is genuinely hard to sit with. So put the pieces of this act side by side, because together they say something that 60 years of headlines have quietly got backwards. A hot tub of water measured against every ocean on Earth. That is the fraction of the search space examined. A handful of nearby stars, watched for hours at a time, on the assumption that anyone out there transmits continuously and in our direction. Our own planet detectable only in rare flashes, from one angle, with decades of nothing between them. And the loud century closing as efficiency does what efficiency always does. Now say the phrase again, the one you have heard 100 times. The great silence. It is not a silence. It is an absence of measurement. And those are different things in a way that matters enormously. A silence is a result. An absence of measurement is a blank where the result would go, and a blank cannot support any conclusion at all, comforting or otherwise. Yet look at what the blank has been asked to carry. It has been used to argue that we are alone, that something is killing civilizations, that we are early, that we are special, that we are watched. Every one of those arguments rests on a finding nobody ever made. Do you see the shape of the mistake? We took the edge of our own reach and called it the edge of the world. Does that mean the problem dissolves? No. And this is where the first door closes rather than opens. The arithmetic that started this has not gone anywhere. The galaxy is still old enough and crowded enough with worlds that somebody should have crossed it by now. Removing the silence as evidence does not remove the gap. It only removes the one explanation people found soothing, which was that the question might be premature. The question is not premature. We simply have not been able to ask it properly, and for 6 decades we have been treating our own inability to ask as though it were an answer coming back, which leaves you somewhere less comfortable than where you started this hour. The search may barely have begun. Whatever is out there was never ruled out, only unexamined, and the signal may arrive next year or next month. And that possibility exposes something nobody wants to look at directly. Suppose it arrives tomorrow, in your lifetime, on an ordinary weekday. Who exactly picks up? Ask a simple question and watch how quickly it stops being simple. A confirmed signal arrives. Who announces it, and what do they say? There is a document that claims to answer this. It is called the Declaration of Principles Concerning Activities Following the Detection of Extraterrestrial Intelligence, drafted in 1989 by the International Academy of Astronautics. It reads well, and you would likely approve of every line. Verify before announcing. Inform the relevant national authorities and the United Nations. Make the data available to the international scientific community. Do not reply on behalf of humanity without global consultation. Now, the part that matters. What legal force does that document carry? None. It is a professional agreement between researchers, not a treaty. No government signed it. No parliament ratified it. Nobody is bound by it. And nobody can be penalized for ignoring it. You have been assuming otherwise. So the protocol you have vaguely assumed exists, the one in your head, is closer to a code of conduct than to a chain of command. And even inside that voluntary arrangement, the wording collapses at the point where it matters most. Consult globally before replying. Through what body? The United Nations Office for Outer Affairs employs a staff smaller than a village school and holds no authority to compel any state to do anything. Consider what verification actually demands in practice. A candidate signal appears at one observatory. Confirming it means independent detection elsewhere, which means telling other institutions, which means the information is now in circulation across multiple countries before anyone senior has decided anything at all. How long does that stay contained? In an era where a graduate student can post a plot from a control room at 3 in the morning, the honest answer is minutes. So the sequence likely runs backwards from the intended one. Rumor, then leak, then confirmation, then whatever governments say afterwards. The declaration assumes an orderly world with a controlled release, and that world arguably has not existed for 2 decades. None of which would matter much if a signal were merely interesting. But a signal is not merely interesting, and the moment it is confirmed, someone is going to want to answer it. That is where the absence of any law becomes something harder than an oversight. Try to name the office. A signal is confirmed, verified, real. Which desk on this planet is responsible for what happens next? Take a moment. Because most people assume the answer exists somewhere just outside their knowledge. You will not find it. Not in the United States, not in China, not in the European Union, not anywhere. No statute in any country designates an agency to receive, assess, or respond to contact. No budget line funds it. No official holds it in their job description. The desk you were picturing is empty. Compare that with the threat we did organize around. Asteroids. In 2016, NASA formally established a Planetary Defense Coordination Office. It has a director, a budget, a mandate, and a defined relationship with other agencies. When a rock was found in late 2024, with a small chance of striking Earth in 2032, the machinery engaged immediately. Observations were prioritized, the estimate refined, the risk fell away. That is what preparedness looks like when it genuinely exists. Now, hold the two side by side. For a rock, we built an office. For contact with another intelligence, we produced a 4-page statement of good intentions with no signatory who can be held to it. Why the difference? Partly because one threat is quantifiable and the other likely is not. Mostly because one has a failure mode a politician can picture and the other does not. Ask yourself which of the two would actually change your life more. There was a moment when it nearly went differently. NASA ran a genuine search program through the 80s and into 1992. It lasted roughly a year in operation. In 1993, a single senator moved to strip the funding, arguing publicly that no little green men had been found, and the program was cancelled. Everything since has been privately funded, which probably explains more than it should. So the institutional position appears to be this: the only sustained effort to detect the most consequential event in human history runs on donations, and the plan for what to do if it succeeds is a document nobody signed. You're probably assuming that a discovery of that magnitude would force the structures into existence overnight. Would it? That assumption has been tested, not with signals, but with other events we saw coming for decades. Suppose the structures did appear. Suppose the meeting happens, the seats are filled, and the question on the table is what to send back. You are in that room. What can you actually negotiate? Almost nothing, and the reason is not political, but geometric. Take a target 100 light years away, which is close by the standards of this search. Your message leaves and arrives in a century. If they answer instantly, that answer reaches Earth a century after. One exchange, 200 years. Ask a clarifying question and you have spent 4 centuries on 2 sentences. Every form of negotiation you have ever seen depends on iteration. You say something, watch the reaction, and adjust. Offers move, misunderstandings get repaired within minutes. Remove the reaction entirely, and what remains is not negotiation, it is declaration. So whatever we send has to be complete on the first attempt, unambiguous without clarification, and correct without feedback. Final too, because whoever composed it will likely be dead long before any consequence arrives. Now consider who holds the file across that gap. A message sent this year returns an answer around the year 2200. Which organization existing today do you expect to be operational then, with continuity of purpose and access to the original context? Look at the actual track record. Very few institutions on Earth have run continuously for 2 centuries, with intact intent. Governments reorganize, agencies are absorbed, and archives migrate into formats nobody can read. The average multinational corporation probably does not survive 50 years. The average constitution lasts under 20. Engineers borrowed a term for this from the nuclear waste problem: long-term stewardship. How do you communicate a warning to people 10,000 years from now who share no language with you? Serious effort has gone into that question, and no satisfactory answer has apparently emerged. Interstellar dialogue is arguably that problem doubled. You must maintain meaning across centuries on your side while assuming they maintain it on theirs. So the picture changes shape. The difficulty was never finding them. It may be that a conversation, in any sense you would recognize, is simply not available to us. And if that is true, then something ugly follows about the messages we have already sent. You may be thinking that none of this matters much. An event that large would force the world to organize itself. Money would appear, committees would form, and the machinery would assemble because it had to. Is that belief reasonable? It has been tested, not with signals, but with the closest thing available. Consider how preparedness actually performed in the one case where the planning had genuinely been done. Pandemic response plans existed in most developed nations. Simulation exercises have been run repeatedly through the 2000s and 2010s with published findings and specific recommendations. Stockpiles were specified and reporting chains were mapped. On paper, humanity was ready, and you would have signed off on those documents yourself. Then the event arrived, and what happened next is within your own memory. Borders closed at different times on different logic, agencies contradicted each other inside the same week, and countries with the most detailed plans did not obviously outperform countries with none. The point here is not blame, and it is not that people behaved badly. The mechanism is more uncomfortable than blame. A plan is a description of coordination, not coordination itself. Under time pressure, with incomplete information and competing national interests, written plans likely degrade into whatever the fastest actors decide on their own. Now, apply that mechanism to contact. Which pressures get worse? All of them. Information incompleteness is far higher, because nobody can independently verify what a signal means. National interest is sharper, since being first to decode arguably carries real advantage. And the timeline is stranger. There is no deadline-forcing agreement, which sounds better and is not, because deliberation without a deadline tends to produce nothing at all until someone acts alone. So what should you actually expect? Probably not global consultation. A decision made by whoever holds a transmitter, a motive, and no obligation to ask anyone. That is not a hypothetical failure. It has already happened, more than once, and those transmissions are crossing open space right now with nobody able to recall them. But before that, there is one more thing worth knowing about the institutional gap. Somebody finally noticed it. In 2022. In 2022, 33 years after the declaration nobody signed, somebody finally tried to build the thing that was missing. The SETI Post-Detection Hub was established at the University of St Andrews in Scotland, led by a computer scientist named John Elliott. Its stated purpose is straightforward and slightly astonishing when you say it out loud: to develop the protocols, the analysis frameworks, and the social and legal preparation that should have existed since the search began. Read that again, slowly. The framework for handling contact was started in 2022. The search itself began in 1960. Does that ordering strike you as sane? 62 years of listening before anyone assembled a serious effort to answer the obvious follow-up question. What do we do if the listening works? And look at the scale of what got assembled. Not an agency and not a treaty body. A research hub inside a university, drawing on volunteers and academic time across several institutions, with no enforcement power and no guaranteed funding beyond the next grant cycle. The work is careful and the people are serious, and that is not the issue. The issue is proportion. Would you consider that a matched response to the problem? Set it against comparable questions. Nuclear weapons produce treaties, inspection regimes, permanent international bodies, and dedicated national commands, all within roughly 15 years of the first detonation. Asteroid risk produced a coordination office with a standing budget. Even space debris, a genuinely mundane engineering nuisance, has more institutional weight behind it than the question of what humanity says to another intelligence. Why does the gap persist? Likely because the event has never happened, and institutions tend to form around events rather than possibilities, which is a reasonable explanation and arguably no comfort at all, since the entire point is that this event happens once and cannot be rehearsed. So consider where that leaves you. There is no office, there is no law, there is a voluntary code from 1989 and a university hub from 2022, and between them sits what may be the largest unaddressed decision in the history of this species. And this is still the optimistic branch. This branch assumes somebody is out there to hear from. Stack the second act up, and look hard at what you are actually standing on. 66 years of searching. A voluntary declaration with no legal force. No national agency anywhere with the authority to receive a signal. No mechanism that could deliver a global reply even if global agreement existed. A geometry that makes conversation, in the ordinary sense, physically unavailable. A track record showing that written plans dissolve under real-time pressure. And a single university hub, founded 3 years ago, carrying the whole institutional weight of the question. That is the readiness. All of it. Does anything on that list look like a system to you? Now, put the two acts together, because the combination is worse than either half. The first act showed that the silence is not a finding, which means detection remains genuinely possible, and may simply be a matter of when. The second act shows that we have built essentially nothing to handle it. Those two facts point in the same direction, and the direction is unpleasant. The more likely detection becomes, the more the absence of preparation matters. We spent 6 decades quietly improving the odds of an event we made no arrangements for. Ask yourself what that pattern resembles anywhere else in life. Would you accept it from an airline? From a hospital? Somehow it has been acceptable here, likely because the event felt permanently theoretical, like a thing that happens in other centuries. But notice what has quietly happened to you in the last hour. You arrived thinking this was a question about them. Twice now it has turned into a question about us, about what we searched and failed to search, about what we built and failed to build. Neither turn required a single alien to exist. Hold that, because the pattern is going to repeat, and the next turn is the hardest one in this entire subject. We have been assuming there is someone to detect. That assumption has never been tested either. And in 2018, 3 researchers at Oxford ran the numbers honestly for the first time, without the comfortable shortcuts everyone had been using since that chalkboard in 1961. What they found does not make you safer. It makes the room colder, and it removes the last version of this story, where being alone was the gentle outcome. In 2018, 3 researchers at the Future of Humanity Institute in Oxford published a paper with a title that sounded almost dismissive: Dissolving the Fermi Paradox. Anders Sandberg, Eric Drexler, and Toby Ord were not proposing a new alien behavior. They were suggesting that everyone had been doing the arithmetic wrong for 57 years. Here is the mistake, and you have almost certainly made it yourself in another context. When people use the Drake equation, they pick a value for each term, their best guess. Then they multiply the guesses together and treat the product as an estimate. Does that sound like the obviously correct procedure? It feels like one. It is not. And the reason matters more than anything else in this act. Some of those terms are not uncertain by a factor of 2. They are uncertain across enormous ranges. Take the probability that life begins on a suitable world. Nobody has a second example to compare against, and the Oxford team had to model that term with a spread of some 50 orders of magnitude. Not 50%. 50 zeros between the pessimistic end and the optimistic end. Try holding that in your head for a second. What does a best guess even mean for a quantity like that? Picking a middle value implies a confidence nobody actually has. You are not choosing an estimate at that point. You are choosing a mood and then dressing it up as arithmetic. So the Oxford team did the thing the equation should have had from the start. Instead of one number per term, they fed in the full published range of scientific uncertainty for each of the 7. Then they ran the multiplication millions of times, drawing randomly from those ranges, and looked at the shape of the results rather than at one output. That method has a name, and it is not exotic. Engineers use it to check whether a bridge survives a range of loads. Insurers use it to price hurricane damage before a hurricane exists. It is standard practice everywhere that uncertainty runs genuinely large, which is to say, almost everywhere serious money is at stake. It had apparently never been applied properly to this question. Why not? Probably because the equation looked like it was already giving answers. And when they ran it, the distribution that came out was arguably not the one anybody was expecting. Picture the output as a graph. Along the bottom, the number of communicating civilizations in our galaxy. Along the side, how often that answer came up across millions of runs. What shape would you expect? Probably a hump somewhere in the middle. A most likely value, with tails on either side. That is what a normal distribution looks like, and it is what most people carry in their heads when they hear the word average. That is not what appeared. What came out was spread across so many orders of magnitude that the graph had to be drawn on a compressed scale to fit on a page at all. And a substantial share of the runs landed at a value below 1. Below 1 means 0. It means nobody else in this galaxy, at all, anywhere, right now. The headline figure from that paper is worth stating carefully. Given the actual state of scientific uncertainty as published, There is a meaningful probability, roughly a third when you look at the galaxy, that we are the only technological civilization in it. Extend the question to the entire observable universe, and the probability of being alone apparently remains far from negligible. Now, be precise about what that does and does not claim. It is not evidence that we are alone. Nobody measured anything new, and no telescope was involved. What it shows is subtler and harder to dismiss. Our existing knowledge is so thin that being alone was likely always sitting inside the range of reasonable answers, and the habit of plugging in middle values had been hiding it from view. Which means the paradox may be smaller than advertised. If the honest calculation already permits an empty galaxy, does an empty sky need any exotic explanation? No hunters, no filters, nobody hiding, just a universe where the relevant probabilities happen to be very small. Should that be a relief? It reads like one for about a minute. Then something else surfaces. Then you notice what has quietly been removed. Every disturbing solution we are about to examine at least assumed company. Something out there, somewhere, doing something. This branch takes the company away and leaves the disturbing part standing, because being alone is not the safe answer people assume it is. It may be the least survivable position in the whole set. To see why, you have to look at what it took to produce us. To understand why being alone should frighten you, look at the road that produced you. Not the story version, the timing. In 1983, the Cambridge cosmologist Brandon Carter published an argument that is still one of the most quietly disturbing pieces of reasoning in this field. He was not writing about aliens at all, but about a coincidence in the timing. Carter noticed two numbers that had no business resembling each other. The time it took life on Earth to produce an observer capable of asking these questions is roughly 4 billion years. The total time our sun will remain stable enough to support that life is roughly 10 billion. Those two figures sit within a factor of a few of each other. Why should they? There is no physical connection between how long a star burns and how long biology takes. Stellar lifetime is set by mass and fusion, while evolutionary timing is set by chemistry and chance. They are independent processes, and when two independent processes hand you similar durations, that usually means something has been missed. Would you accept that as chance? Carter's explanation was uncomfortable. Suppose the emergence of an observer requires a series of steps, each individually very unlikely. Not difficult in the way climbing a mountain is difficult, unlikely in the sense that each one might typically require far longer than a star provides. Under that model, something strange happens to the timing. If the steps are hard enough, then the only planets where all of them complete are the rare ones where every step happened to occur early, by luck, in a row. And on those planets, the completion tends to land near the end of the available window, because that is where the odds finally catch up, which is more or less exactly where you find yourself. Complex life appeared here with roughly 1 billion years of habitable time left out of 10. Late, right up against the wall. So how many hard steps were there? Candidates get proposed and argued over. The origin of life itself, oxygen-producing photosynthesis, the complex cell, multicellular organisms, then whatever produced a species that builds instruments. Estimates for the number of genuinely improbable steps range from a handful to a dozen. And the number matters enormously, because it sets how often this happens anywhere else. Look at the actual timings, because the pattern in them is what gives the hard steps model its weight. Earth formed roughly 4.5 billion years ago. The surface became survivable somewhere around 4 billion. And the earliest reasonable traces of life appear almost immediately after that, in geological terms. Life started fast, and that looks encouraging when you first read it. Then nothing much happens for an extraordinarily long time. Single-celled organisms, and only single-celled organisms, for roughly 2 billion years. Half the history of this planet spent as microbial films, with no visible progress toward anything else. 2 billion years. Does that sound like a process straining to produce you? Oxygen-producing photosynthesis arrives, and eventually poisons the atmosphere for everything that had adapted to its absence. The complex cell, the kind your own body is built from, appears just once in the entire fossil and genetic record, not repeatedly across different lineages. Once, apparently. Every plant, animal, and fungus that has ever lived descends from that single event. Multicellular life then takes another billion years to become anything you would notice. Animals with body plans show up around 500 million years ago. Land vertebrates later. Primates far later. Technology in the last 10,000 years, which on this timeline barely registers as a rounding error. Now put that sequence against the clock. The sun brightens as it ages. In roughly 1 billion years, the increase in output will likely push Earth past the point where liquid water survives on the surface. That is your remaining window. 1 billion out of the 10. So the honest summary reads like this. Life appeared quickly, then spent 4 billion years crossing a small number of barriers, and finished with about 10% of the available time left. Does that look like a process with margin in it? Run this planet again with slightly different look at any of those barriers, and the sun brightens before anyone is here to notice. Which brings the two threads together? Where does that leave the odds? The Oxford calculation says being alone sits comfortably inside the honest range. Carter's timing suggests why. And now the branch closes, because people reach for the same consolation every time. Here is where most people reach for the obvious consolation. Fine, we're alone, so the galaxy belongs to us. No competitors, no rivals, nobody to fight over resources with. 200 billion stars, and not one other claim on any of them. You may have felt that thought forming already, and it deserves to be taken seriously, rather than waved away. It fails, but it fails in 3 separate places, and each one costs you something different. The first failure is simple and mechanical. Being alone does not make the distances any shorter, and nothing about an empty galaxy improves our propulsion, our shielding, or our ability to keep a human body alive for decades in transit. The nearest star remains 4 light years away, whether or not anyone lives there. An empty house you have no way of reaching is not an inheritance. The second failure is about what the emptiness would imply. Follow the logic backwards for a moment. If we are alone, the most likely reason is that the steps required are brutally improbable. But you are the output of those same steps. That is not a statement about aliens at all. It is a statement about how narrow the process was that produced you, and narrow processes rarely produce robust results. Would you trust a machine built that way? The third is the one that actually matters: redundancy. Think about how any system survives a failure. Backups, spares, multiple independent copies, so that losing one does not lose the function. So what redundancy exists for a technological civilization in an empty galaxy? There is none. Not reduced redundancy. None at all. If we are alone, then every discovery ever made, every question ever asked, every piece of understanding this universe has generated about itself, sits in exactly one place. One planet, one species, one narrow band of chemistry that has to keep working without interruption. And the harder version of that question: if we fail, does it happen again? Carter's model suggests not, at least not here. 4 billion years to run the sequence once, and roughly 1 billion left on the clock. The process does not get a second attempt inside the window that remains. So the emptiness is not an inheritance waiting to be claimed. It is something a great deal more exposed than that, and the exposure has a name. Follow that exposure to where it actually leads, because there is a detail here that most people never connect. Remember the name Toby Ord. He was likely the least famous of the 3 authors of the 2018 paper showing that being alone sits well within the honest range of the calculation. 2 years later, in 2020, he published a book about a different subject entirely: the risk that this century ends us. The estimate he arrived at, after working through nuclear war, engineered pathogens, climate tipping points, unaligned artificial intelligence, and the rest, was roughly 1 in 6. Would you board a plane on those odds? Not 1 in 6 that things go badly. 1 in 6 that humanity's future is permanently destroyed or curtailed within 100 years. Now hold those two pieces of work side by side. The same researcher, using the same methods, published one paper suggesting we are plausibly the only technological species in this galaxy, and one book estimating a meaningful chance we do not survive the next 100 years. Do those two findings belong to separate subjects? They do not. They multiply. What does it mean if both are roughly right? It means the entire experiment might terminate on a single planet in a single century from causes we generate ourselves, not from hunters, not from filters imposed by physics, from ordinary institutional failure of the kind you can already watch happening in your own lifetime. And here the branch closes properly, because you can see what it removes. Every frightening solution we have left to examine has one hidden comfort buried in it. If something out there is expanding, or sleeping, or watching, then at least the universe contains other minds. Whatever happens to us, the project probably continues somewhere else. Take that away, and the arithmetic changes shape. If we are the only ones, then our survival is not one outcome among many. It is the whole thing. That is what people miss when they say, being alone is the boring answer. Boring would mean low stakes. This is the opposite. Being alone arguably raises the stakes on every decision made on this planet to a level nothing in our history prepared us for. So, the third door does not open onto safety either. It opens onto a responsibility nobody asked for, that no institution is holding, and that you personally have a share of whether or not you want one. Set the third act down and look at what it actually did to your position. You came into it expecting the gentlest branch of the whole subject. Nobody out there, nobody coming, nothing to defend against. Where is the horror in an empty room? What emerged instead was a calculation showing emptiness had been sitting inside the honest range all along, a timing argument explaining why, and a fossil record that reads like a sequence of near misses. Then the redundancy question. If we are the only ones, there is no backup anywhere. None. And the same researcher who helped show we are plausibly alone also put roughly 1 in 6 on this century ending us. That is the third door. There is no monster behind it. There is a mirror, a very short list of spare parts, and no supplier anywhere in 200 billion stars. Notice what has happened to the shape of this. 3 branches examined, 3 entirely different mechanisms, and the same structure underneath each one. Did you catch it as it went past? The first act said our silence was a measurement failure rather than a finding. The second said our institutions were simply absent. The third said our margin for error was non-existent. At no point in 3 hours of argument has a single alien been required to make any of it work. You're watching a pattern assemble in real time, and the pattern has nothing to do with the sky. But the third act raised something it did not answer, and it may be the strangest single fact in this entire subject. Carter's timing argument said we arrived near the end of our own star's window. That is one clock. There is a second clock, much larger, and on that one, we are not late at all. Measured against the lifespan of the universe itself, you are absurdly, almost inexplicably early. Star formation will continue for trillions of years. The overwhelming majority of habitable worlds that will ever exist have not formed yet. Most of the life that will ever appear has not appeared, and will not for an extremely long time. So why are you here now, at the very beginning, on a night when the universe has barely started running? That question has a mathematical answer, and it is a good one. Nobody who works on it appears especially comforted by what that answer implies about the rest of the schedule. In 2016, a Harvard astronomer named Avi Loeb put a question on paper that sounds almost childish until you see the answer. Working with Rafael Batista and David Sloan, he wanted to know when, in the whole history of the universe, life is most likely to appear. Not whether life appears at all, when. Treat cosmic time as the variable and calculate where the probability actually peaks. Nobody had done it that way before. The paper appeared in the Journal of Cosmology and Astroparticle Physics in 2016, and the method behind it is refreshingly direct rather than exotic. Life needs a star that holds steady long enough for chemistry to do its work. So count the stars that will ever exist. Weight each one by how long it burns. Weight it again by how likely it is to hold a habitable world. Then spread the whole thing across the future of the universe and see where the curve rises. The result is not close, and it is not ambiguous. The probability of life emerging does not peak now. It does not peak soon either. It peaks something like 10 trillion years from now. That is roughly 1,000 times the current age of everything that exists. Read that number twice because your intuition will slide straight off it. The universe is 13.8 billion years old. The peak of habitability arrives somewhere around 10 trillion. Are we in the middle of this story? We are in the opening sentence of it. Why so far off? The answer sits in a fact about stars that rarely makes it into popular accounts. Most stars are not like the sun. Roughly 3/4 of the stars in this galaxy are red dwarfs, small, dim, cool, and they burn their fuel with extraordinary patience. Our sun has around 10 billion years in total. A red dwarf can run for 10 trillion. That is not a longer life in any ordinary sense. It is 1,000 times longer, which means one red dwarf quietly outlasts 1,000 consecutive suns like ours. So, the vast majority of habitable time in this universe has not happened yet, and nearly all of it belongs to stars that are still barely getting started on their fuel. Which raises a question you may not want to sit with for long. If life is most likely trillions of years from now, in a future that has not remotely begun, what exactly are you doing here tonight? Try to feel the scale properly, because the numbers stop meaning anything if you only read them. Compress the entire habitable era of this universe into a single calendar year. Every star that will ever form. Every world that will ever cool. Every chance life will ever get, all of it laid out from January through December. Where does the present moment fall on that calendar? Not January. Not the first week of January. The universe as it exists tonight, 13.8 billion years in, likely sits inside the first few minutes after midnight on New Year's Day. Everything you have ever heard of happens in those minutes. Every star you can name and every galaxy in every photograph. All of recorded history, all of biology, the entire fossil record, the formation of the Earth itself, all of it inside those few minutes. And you are standing there in the dark, asking why the room is empty, when the doors have arguably not finished opening. Now, the mechanism underneath that, because the timing is not arbitrary. Stellar lifetime depends almost entirely on mass, and that relationship is brutally steep. Does doubling the mass halve the lifetime? Not remotely. A star twice the mass of the sun burns out roughly 10 times faster. A star half the mass of the sun lasts vastly longer than twice as long. The reason is pressure. More mass means more gravitational compression at the core. More compression drives fusion harder. Harder fusion consumes hydrogen at an accelerating rate. Massive stars are extravagant and probably die young. Small stars are miserly and outlive almost everything around them. Red dwarfs sit at the miserly end of that scale, and they also mix their fuel far more thoroughly than the sun manages. Our star will only ever burn the hydrogen sitting near its core, and the rest is simply wasted. A red dwarf apparently circulates its entire mass through the burning region, which means it eventually uses nearly all of what it has. So the galaxy is stocked overwhelmingly with slow, patient, enormously long-lived stars, and almost none of their habitable time has elapsed. That leaves an awkward position for anyone who wants to explain the silence by saying life is simply rare. If life is rare, why did the one example we know of arrive at the earliest possible moment rather than somewhere in that vast middle? Now put an actual number on how unusual your position is, because a vague word like early does not carry the weight it needs to. Take the total habitable era of the universe and ask what fraction of it has elapsed. On Loeb's figures, the answer is likely somewhere around 1,000th of 1%. Put it in human terms. If the habitable era were a lifetime of 80 years, everything that has ever happened would fit inside the first 20 minutes after birth. Every star, every extinction, every war. Now flip it into a probability. Imagine every observer who will ever exist across that whole span, all of them asking roughly these questions, on their own worlds, under their own stars. Draw one of them at random. What are the odds you draw someone standing at the very beginning? Vanishingly small. And yet here you are, holding that exact ticket. So how do you explain a draw that unlikely? There appear to be only two routes. Either the draw was a genuine fluke, or the ticket in your hand is not the kind you assumed it was. Hold that fork, because we return to it shortly. First, notice how badly this collides with everything else in the subject. Every explanation for cosmic silence that leans on rarity has just acquired a serious problem. If technological life is rare, turning up on maybe one world in a trillion, then the few instances that do occur should be scattered thinly across the whole habitable era. Most should arise in the vast middle or toward the end, when the overwhelming majority of habitable worlds actually exist. Instead, the single example we can actually verify shows up inside the first fraction of a percent before the universe has properly started. Is that what rarity looks like? It is not. Rarity spreads events thinly across the available time. What we are looking at is the opposite pattern. An event clustered at the earliest possible instant. Clustering arguably demands a cause. So one of your assumptions has to break here. Either life is not rare in the way people usually mean, or the future does not contain the observers that calculation predicts it should. Neither option leaves the picture anywhere near where you found it, and there is a version of that second option which is genuinely difficult to look at directly for very long. There is a reply to all of this that sounds like it settles the matter, and you have probably already thought of it. Somebody has to be first. Whoever that turns out to be will look around, see an empty sky, and find their own position strange. No mystery required, no filter needed, nothing to explain. Is that a good answer? It is not a stupid one. It is simply answering a different question from the one on the table. Grant the premise completely. Yes, first observers exist. Somebody occupies that slot. But the question was never whether early observers exist somewhere. The question is whether you should expect to be one of them. Work it as odds. Suppose trillions of observers arise across the habitable era, and a tiny handful arrive in the opening fraction. Pick one at random. Who do you get? Overwhelmingly, you get somebody from the crowded middle, surrounded by other civilizations, on a world orbiting a star that will not form for another trillion years. That is not what happened here. So either something extraordinarily unlikely occurred on this particular planet, or the model producing those trillions of future observers is wrong somewhere. Here is where the objection quietly fails. Saying somebody has to be first explains that the slot is occupied by someone. Does it explain why you were the one standing in it? It does not. Those are different claims, and only the second one needs answering. And there is a standard move in science for exactly this situation. When you find yourself in a position your model says should almost never happen, you do not shrug and call it luck. You start suspecting the model instead. That is precisely what Brandon Carter was doing in 1983. He is often misread as arguing that our existence explains away every awkward coincidence. He was arguing close to the opposite. Observer selection does not dissolve surprise. It constrains which models can be true, and a model that makes your own existence wildly improbable is likely a model with something missing. Apply that reasoning here, and the conclusion is uncomfortable but clean. Something in the standard picture of the cosmic future is probably wrong, and it is wrong in a way that removes almost all of those future observers. And there appear to be only two candidates for what that missing piece is. Take those two candidates seriously, one at a time, and watch carefully where each of them lands. The first possibility is that you are not actually early at all. The trillions of future worlds exist in the star counts, but almost none of them will ever host anything alive. If that is true, the habitable era is not just beginning. It is roughly now, and it is far narrower than those numbers suggested. There is real science behind this, and it is not a convenient excuse. Red dwarfs, the stars carrying nearly all that future time, have problems. They flare violently and often, hitting close orbiting planets with bursts of radiation that can strip an atmosphere away entirely. Their habitable zones sit so close in that worlds they're likely become tidally locked. One face permanently lit, the other permanently dark, with whatever weather that produces. And during their first billion years, these stars pour out intense, high-energy radiation, precisely while any planets around them are still assembling their atmospheres. So the case can be made. Perhaps only stars like the Sun work, and Sun-like stars are a minority that mostly formed early. Perhaps you are sitting near the peak rather than at the opening of the era. But look at what that answer cost you. Does it solve the problem? It means the universe holds far fewer habitable worlds than the raw counts imply, which pushes you straight back into the third act. Fewer worlds, fewer chances, and the loneliness argument gets stronger rather than weaker. Now, take the second possibility. You genuinely are early, and the reason later observers do not dominate the count is that later observers never arrive. Read that carefully, because there are two ways it could happen. Either technological life stops appearing at some point in the future, or it keeps appearing and does not last long enough to be counted. The first version requires something to change about the universe itself. What does the second require? Nothing at all. It only requires that civilizations are short. Which of those does everything so far point toward? Every branch of this has been about duration, our loud century, our absent institutions, our 4 billion year run with 1 billion left on the clock. The word sitting underneath all of it is not rare. It is brief. Sit for a moment with the version where we really are first, because it does something to your situation that has nothing to do with danger or hunters. Think about how you handle any serious problem. You look for precedent. Has anyone done this before, and what happened to them? Every field on Earth works this way. Medicine keeps case histories, engineering keeps failure reports, law keeps rulings. The entire structure of human competence rests on somebody having gone first and left a record. Now, list the problems in front of this species over the next few centuries. Managing a technology that can rewrite biology at will, managing systems that outthink their own designers, managing a closed planetary environment holding 8 billion occupants with rising demand, managing weapons that could arguably end the whole experiment inside an afternoon. For each one, ask the normal question: who solved this before and how? If we are first, the answer is nobody. Not a hard question whose answer exists somewhere and has not been located. No answer exists at all. No civilization has ever crossed this and left notes, because no civilization has ever been here. That is a strange kind of exposure, and it deserves a moment. Every generation before you inherited some accumulated wisdom about the problems it faced. Flawed, incomplete, often wrong, but real. Somebody had at least tried it, and someone had watched what happened. This is likely the first set of problems in human history with no ancestors at all, and they happen to be exactly the ones where failure does not get corrected afterward. And notice what that does to the silence. Up to now, we have been treating it as a question about who else is out there. Read it a different way. Is the silence about company, or is it the absence of a manual? There is no library. There is no worked example. There is probably no older species that got through its own version of this century and could tell you which parts actually mattered. You are the first to attempt it, and the attempt is being made in real time by institutions we already established are not built for it. So the fourth door closes as badly as the 3 before it, and it closes on one specific word: brief, which brings us to the branch that tries to explain why. Look hard at what the fourth act actually established, because it is easy to lose inside numbers that large. The habitable era of this universe has barely begun. The overwhelming majority of stars that will ever support life have not formed. And yet here you are, in the opening fraction of a percent, asking why nobody else has shown up. Two explanations appear to survive scrutiny. Either the future is far less habitable than the star counts imply, which shrinks the universe and strengthens the loneliness case. Or the future genuinely contains almost no observers, which likely means something removes them before they arrive. And within that second option, one version needs no new physics whatsoever. Civilizations simply do not last. That word has now surfaced in every act of this video, and you may not have noticed it accumulating. The loud century that closes after roughly 100 years. The institutions that never formed across 60. The 4 billion year run with 1 billion remaining. And now an observer count that collapses unless technological life is short. 4 different lines of argument using 4 different methods and the same variable underneath all of them. Duration. So the question quietly changed shape while you were watching it. It stopped being where is everybody? It became something narrower. How long does anybody last? And that question has an answer nobody enjoys, because the obvious candidates for what shortens a civilization are all the things you would call success. Growth, expansion, rising consumption, rising energy use, every single metric a species would reach for to measure its own progress. What if those are not the signs of a civilization succeeding at all? What if you have been reading the scoreboard upside down? That is not a moral claim about greed, and it is not an environmental sermon. It is a thermodynamic argument, published in a peer-reviewed journal in 2009, and it says something specific about what probably happens to any species that grows exponentially for long enough. The conclusion is that expansion and long-term survival may simply be mutually exclusive, which would mean the filter is not behind us at all. It would mean we are walking into it at full speed, on purpose, calling the whole approach development. In 2009, 2 researchers published a paper in the Journal of the British Interplanetary Society with a title that sounds almost dull: The Sustainability Solution to the Fermi Paradox. Jacob Hack-Misra and Seth Baum were not proposing hunters, filters, or hiding. They were proposing something about growth, and it may be the most quietly devastating idea in the whole subject. Their argument starts by attacking an assumption almost nobody examines. Every version of this paradox you have ever heard, including the one you carried into this video, rests on the same hidden premise: that a civilization which develops technology will expand outward, continuously, until it fills whatever space is available to it. You accepted that without noticing. Where does that premise actually come from? Not from physics, and probably not from biology. It comes from roughly the last 400 years of European and American history, which is an extremely small sample projected confidently onto the whole universe. Hack-Misra and Baum asked the obvious follow-up question: is continuous exponential expansion actually a stable strategy across cosmic timescales? Or is it a phase that always terminates everywhere for reasons that have nothing to do with choice? And here the argument turns thermodynamic rather than sociological, which is probably why it is so difficult to argue with. Exponential growth means a fixed percentage increase per unit time. 2% a year, say. 2% sounds gentle, almost cautious, the sort of number a finance minister announces with relief. But a fixed percentage has a property that human intuition handles badly. It produces doubling at fixed intervals forever, and doubling compounds beyond anything your intuition will accept. Any quantity growing at 2% a year likely doubles every 35 years or so. 10 doublings multiply it by 1,000. 20 doublings multiply it by 1,000,000. 30 doublings multiply it by 1,000,000,000. So the question stops being whether growth is good or bad. It becomes something far more specific and far less comfortable. How many doublings can a planet physically absorb before something breaks? The answer turns out to be a small number, and the breaking point has nothing to do with running out of anything. The limit that stops a growing civilization is not fuel, and this is where most people's intuition fails completely. You probably assume the ceiling is resources. Oil runs out, minerals run out, and progress stalls until something else replaces them. That framing has been standard since the 1970s, and it is arguably the wrong problem. Here is the actual constraint. Every joule of energy you use, whatever its source, ends up as heat. Not most of it. All of it. Run a factory and the machinery warms. Run a computer and the chips warm under your hands. Light a room and the walls absorb the photons and warm. Energy does useful work on its way through, and then it degrades into low-grade heat. Because that is what the second law of thermodynamics demands of it. There is no exception, and no technology that avoids it. Now put that on a planet. Earth radiates heat into space at a rate set by its surface temperature. If you add energy faster than the planet can radiate it away, the surface temperature likely rises until the radiation balances again. That is not a theory. It is a bookkeeping identity. Does that sound like a climate argument? It is not one. This has nothing to do with carbon dioxide or greenhouse gases, and it would happen with perfectly clean fusion reactors running on seawater. In 2011, an astrophysicist at the University of California in San Diego, Tom Murphy, ran this calculation properly and posted it on his blog, Do the Math. He took the historical growth rate of human energy consumption, roughly 2 and a bit% a year sustained over centuries, and asked a simple question. When does waste heat alone make the surface uninhabitable? The answer is around 400 years, not 400,000 years. 4 centuries at the rate we have actually maintained, using any energy source you care to name. Solar, fusion, antimatter, it makes no difference, because the constraint is on the output side rather than the input. Does that sound like a distant problem? 400 years ago, Newton had not published anything, and nobody had built a working steam engine. On the timescale of a civilization, that is nothing at all. So growth on a planet apparently has a hard ceiling, set by physics rather than by policy or willpower, which leaves exactly one apparent escape route, and it fails too. Follow the numbers past the planet because the escape route everyone reaches for is space, and it does not work either. The obvious reply to a planetary heat limit is to leave. Build orbital habitats, mine asteroids, move industry off the surface, give a growing civilization the whole solar system, and surely the problem disappears. Does it though? Run the same exponential forward, and watch how quickly that room fills. Murphy carried the calculation further out. At the same growth rate, roughly 2 and a bit% a year, a civilization likely consumes the entire energy output of its star in about 1400 years. Every photon the sun produces in every direction, captured and put to work. What comes after that? Nothing. That is the theoretical maximum for a single star system. 1400 years. That is less time than has passed since the fall of Rome, and you can name several institutions older than half of it. Keep going, and it gets stranger. At that same rate, the entire energy output of the Milky Way, every star in a galaxy of 200 billion, is consumed in roughly 2,500 years. Read that again, slowly. 2,500 years from one planet to an entire galaxy, if the exponent simply holds. Does that feel like a physical possibility to you? Now you can probably see the shape of the trap. Exponential growth does not run into a wall slowly. It runs into every wall almost immediately, one after another, because each new resource base buys you only a fixed number of doublings before it too is exhausted. Doubling the available energy buys 35 years. Multiplying it by 1,000 buys 350. Multiplying it by 1 billion, which is the difference between one planet and a galaxy, buys around 1,000. That is the whole point, and it is arguably why the escape into space does not save the strategy at all. Space is enormous, and the exponent does not care how enormous it is. You cannot outrun a doubling curve by finding a bigger container. So, any civilization attempting indefinite exponential growth apparently reaches hard physical limits within a few thousand years of starting. Not a few million years, a few thousand, which means every civilization faces the same fork, and the fork has only two branches. You have an objection ready, and it is the strongest one in this entire video. Every prediction of this shape has failed. Malthus said population would outrun food in 1798, and it did not. The Club of Rome said industrial society would hit limits by 2000, and it did not. Peak oil arrived, and then left again. Every time somebody draws an exponential curve and points at a wall, human ingenuity apparently finds a way around it. Why should this time be different? That record is real, and it deserves respect rather than a wave of the hand. So look closely at why those predictions failed, because the reason matters more than the failures themselves. Every one of them was about inputs. Running out of food, running out of oil, running out of ore. And input problems have a reliable solution, which is substitution. When one source becomes scarce, you find another, or you use less of it per unit of output, and the ceiling quietly moves outward. Now compare that with what we just described. The waste heat limit is not an input problem, it is an output identity. Whatever energy you use, from whatever source, arrives as heat on the other side of the process. There is no substitute available for the other side. Can efficiency save it? Only partly, and here the history turns against the optimistic reading. In 1865, the economist William Stanley Jevons studied coal use in Britain and found something that still surprises people. Improvements in steam engine efficiency did not reduce coal consumption, they increased it. Cheaper power meant more uses became worthwhile, and total consumption rose faster than efficiency improved. That pattern has likely repeated with lighting, with computing, and with transport for 160 years running. So efficiency does not oppose growth, it has historically fueled it, and efficiency has a flaw beneath it. Thermodynamics sets minimum energy costs for physical operations, and you probably cannot go below them regardless of engineering skill. Which leaves the strongest objection in this video standing on nothing very solid. Technology beat the input problems brilliantly, repeatedly, and for centuries. That is arguably not evidence it can beat an accounting identity. So what does happen to a civilization that reaches this point? Here is where Hack Misra and Baum turn the whole picture inside out, and it is worth watching carefully because the move is elegant. Every civilization reaching this ceiling apparently faces exactly two options. Keep growing, hit the physical limits within a few thousand years, and collapse. Or stop growing, restructure everything around a steady state, and continue more or less indefinitely. Now ask yourself, which of those two you would be able to see from where you are sitting? A growing civilization is loud. It builds structures, radiates waste heat, expands visibly outward, and starts consuming the stars around it. It is exactly the thing every search has been looking for since 1960. And on this argument, it likely lasts a few thousand years before the exponent finishes it. A steady-state civilization is almost perfectly invisible. It uses a fixed amount of energy year after year. It does not expand into anything. It builds nothing on a scale that alters a star. It generates no expansion front, no megastructure, and no growing thermal signature for anyone to find. And it may quietly last for millions of years. So run the arithmetic on what a telescope actually catches. If loud civilizations last 3,000 years and quiet ones last 3 million, then at any given moment the galaxy contains 1,000 quiet civilizations for every loud one. And the loud ones are the only kind we know how to detect. Do you see what that does to the silence you started this video with? The empty sky is not evidence of absence. On this reading, it is evidence of maturity. A galaxy full of civilizations that solved the growth problem would look precisely like a galaxy with nobody in it. Why? Because solving the growth problem apparently means becoming undetectable as a side effect. And the only ones we could detect are the ones still inside their brief, doomed, expanding phase, which raises the question this act has been building toward from the first sentence. Which kind are we? You already know the answer. Every economy on this planet is structured around growth. Every metric of national success measures throughput going up rather than holding steady. We are, tonight, in the loud phase. And the loud phase is the one that, on this argument, does not have a long future ahead of it. Take that fork seriously for a moment, because it lands somewhere personal. Suppose the argument is right. Suppose survival past a few thousand years likely requires abandoning growth entirely and running flat permanently. What would your species have to change to manage that? Start listing, and the list gets uncomfortable faster than you expect. Compound interest assumes growth. Lend money at any positive rate and repayment requires more value existing later than exists today, which is an exponential written into a contract. Pension systems assume growth because obligations to future retirees get funded out of future output. Equity valuation assumes growth too. What is a share price, if not a bet that earnings will be larger later? None of those three are policies you could vote out. They are the load-bearing structure of every developed economy on this planet, and each one is mathematically an exponential curve wearing a suit. Now add the political layer on top. A government presiding over a flat economy is, by every measure currently in use, failing at its job. There is no vocabulary for success without growth in it. There has never been an election won on a promise of steady state. So the transition this argument requires is not a policy adjustment. It is a replacement of the operating logic underneath finance, government, and expectation, carried out voluntarily before the consequences arrive. How often does a civilization do something like that on purpose? You can probably answer that from history alone, and you will not enjoy the answer. Societies restructure after collapse, rarely before it. The change tends to follow the catastrophe rather than prevent it. And this is the point where the fifth act stops being about aliens and becomes something else entirely. Every metric you have been taught to read as progress, rising output, rising energy use, expansion into new markets and new territories is on this argument arguably the signature of a civilization entering its terminal phase. Not because growth is immoral or greedy, because growth is an exponential, and exponentials always terminate somewhere. The uncomfortable question is not whether we could stop in principle. It is whether anything that evolved out of competitive biology anywhere ever has. So bring the fifth act down to its landing, because it does something to the great filter that almost nobody expects. The standard framing of it runs like this. Somewhere along the road between dead matter and a galaxy-spanning civilization, there is a single step that almost nothing survives. Either that step is behind us, in which case we are extraordinarily lucky to be here, or it sits ahead of us, in which case we are extraordinarily doomed. People argue endlessly about which of those two it is. Almost nobody stops to ask what the step actually consists of. This act suggests an answer, and it is stranger than any catastrophe. What if the filter is not an event at all? What if it is a transition? Specifically, the transition from a growth-based civilization to a steady-state one, made deliberately, made early, before the physical limits arrive rather than after, and made by a species whose entire institutional structure quietly assumes the opposite. Look at what that reframing does to your position. A filter made of asteroids or plagues is bad luck, and bad luck is survivable in principle by anyone. A filter made of a required voluntary restructure is a different animal. It does not kill you. It asks something of you, and apparently almost nobody manages to do it. That is worse because there is no equivalent of getting lucky. And notice how this branch answers the silence without any of the exotic machinery. No hunters, no sleeping empires, no prison walls, just an exponential, a planet, and the second law of thermodynamics, all three of which are already sitting in a first-year physics textbook. The galaxy may be full of civilizations that made the transition. They would be quiet because quiet is what success looks like from outside. and the same galaxy may be scattered with the remains of the ones that did not manage it, each lasting a few thousand loud years before stopping. Which leaves one question still standing, and answering it opens the next door. If a civilization stops growing outward, what on earth does it do instead? Something has to absorb all that accumulated capability. And there is a branch of this subject arguing the answer is not outward at all. That the direction it takes is one you cannot follow with any telescope ever built. There is an assumption buried underneath everything you have heard tonight, and it has now survived 5 full acts without anybody challenging it once. The assumption is direction. Every version of this puzzle you have met takes for granted that an advanced civilization goes outward. More territory, more stars, more physical reach, spreading like something poured onto a surface. When we ask where everybody is, what we are really asking is why nobody has arrived here yet. The verb is always arrive. In 2011, a systems theorist named John Smart published a paper in Acta Astronautica. His proposal was simple. The direction is wrong. His argument is called the transcension hypothesis, and it starts from a pattern in how complex systems apparently develop. Look honestly at the history of technology on this planet. Ask what actually improved over time. Was it size? It was density. The first electronic computers filled entire rooms and consumed enough power to dim a neighborhood. The device in your pocket outperforms all of them by a factor nobody in that era would have accepted, and it fits inside your hand. Every generation of that technology got smaller, faster, denser, and more efficient. Not one generation got physically bigger, and you have watched this happen in your own lifetime. Smart's claim is that this pattern is probably not an accident of silicon. It is what happens whenever a system optimizes for capability rather than volume. He calls it compression across space, time, energy, and matter, and he argues it likely applies at every scale we can currently examine. Now extend that trajectory. If a civilization keeps compressing for a few thousand years, where does it likely end up? Probably not spread across 1,000 star systems, concentrated instead. Smaller, denser, faster, using less space rather than more, until it occupies a volume that would be effectively impossible to notice from outside. That reframes the entire question in a distinctly awkward way. We have been searching for something enormous. Every survey, every megastructure hunt, every search for expansion fronts quietly assumes that advanced means big. What if advanced means precisely the opposite of big, and 6 decades of searching used entirely the wrong instrument for the wrong target? Ask why a civilization would go inward rather than outward, because there is a specific physical reason, and it has nothing to do with preference. The reason is time, not how much of it you have, but how fast you run through it. Consider what happens to a mind that thinks faster. Human neurons fire at a few 100 times per second at absolute best, and a signal crosses your brain in milliseconds. Now, suppose that process migrates onto a substrate running 1,000,000 times quicker. Is that exotic? Not particularly. It is roughly the gap between biological signaling and electronics that already exist. What changes when that happens? Everything about distance. Your subjective second now holds what used to be 11 days of thought. A conversation that took an hour now stretches into a subjective century. And light, which you used to think of as instantaneous, becomes agonizingly slow. Run the numbers on that properly. Light crosses from Earth to the Moon in about 1¼ seconds. To a mind running 1,000,000 times faster, that delay feels like 2 weeks. A message to Mars and back, 20 minutes at light speed, becomes roughly 40 years of waiting for a reply. Now try an interstellar distance. The nearest star sits 4 light years away. To that same mind, a single exchange with anyone there costs something on the order of 8 million subjective years. Do you see what that does to the whole idea of a galactic empire? Distance is probably not merely inconvenient for a fast civilization. It is fatal to coherence. Any structure spread across multiple star systems simply cannot think as one thing. Its parts drift, diverge, and arguably become separate civilizations, because the communication delay exceeds any reasonable attention span by many orders of magnitude. So expansion carries a cost that rarely gets mentioned in any of this. It buys you resources, and it destroys unity. The faster you think, the worse that trade becomes, and there is no engineering fix for it, which suggests something badly counterintuitive. The optimal strategy for a very advanced civilization may be to get smaller and closer together, rather than larger and further apart, and there is a hard physical limit on how far inward that can go. It is not where you would guess. There is a ceiling on how far inward any of this can go, and finding it produced one of the strangest results in modern physics. In the 1970s, the physicist Jacob Bekenstein was working on black holes. He derived a limit on information. Not a practical limit about current technology. A hard one, set by the geometry of space. The result is that any region of space can hold only a finite amount of information. And that amount apparently depends on the surface area of the region, rather than on its volume. Read that twice because it is deeply strange. You would expect capacity to scale with volume, the way a warehouse holds more than a closet does. It does not. Capacity scales with the boundary instead, as though everything inside were written on the surface. Does that sound like a universe built the way you assumed? What does that mean for a civilization compressing itself? It means there is a maximum. Push enough information and energy into a small enough region, and you probably do not get a better computer. You get a black hole. So the inward path has a destination, and that destination turns out to be a specific physical object. Smart's paper says this openly. He argues the endpoint is something with black hole density. That is why he thinks advanced civilizations vanish from view. Now, is any of this testable, or is it philosophy with equations attached? In 2012, 3 physicists, Silas Bean, Zora Davoudi, and Martin Savage, published an approach that suggests it might be. Their work came out of lattice calculations. That is the standard technique for simulating the strong nuclear force on supercomputers, and it works by dividing space-time into a fine grid. Their observation was that any computation of physics on a grid leaves a signature. The grid spacing imposes a maximum energy, and particles arriving at that ceiling would likely show a directional preference tied to the grid rather than to space itself. They proposed looking for exactly that signature in the highest energy cosmic rays reaching Earth. So, the question of whether reality has a computational flaw is not purely philosophical. There is an observational test attached to it, sitting in the literature, waiting for somebody with enough cosmic ray data. And that opens something considerably more disturbing than a vanishing civilization. Work out what a civilization actually buys by going inward, because from the outside, the whole move looks like surrender. You lose territory. You lose resources. You lose every star you might one day have reached. In exchange, you get a smaller volume and a faster clock, which sounds like a poor swap. That sounds like a bad trade until you count what the faster clock is worth. Take 2 civilizations of equal capability. Let both of them run for 1 million years of ordinary external time and see what each one ends up with. The first one expands. It reaches 1,000 star systems, controls enormous resources, and thinks at biological speed because that is what bodies do. Over 1 million years, it experiences exactly 1 million years. The second one compresses instead. It occupies a region you could lose inside an asteroid belt, draws on a tiny fraction of a single star, and runs 1 million times faster than biology allows. Over the same million external years, it experiences 1 trillion years of subjective time. So, which of the two has lived more? Not metaphorically, literally more. The compressed civilization has more experience, more thought, more of whatever it happens to value, by a factor of 1 million, while occupying almost none of the available space. And this quietly reframes something that has sat unexamined all evening. We keep treating expansion as the obvious measure of a civilization's success. Bigger territory, more stars, more visible presence in the sky, but expansion measures extent. and extent may simply not be what a mature civilization optimizes for. If what you want is duration and depth of experience, compression apparently wins by orders of magnitude, and it wins without needing anything to travel faster than light. Look at what that does to the silence. A civilization following this path is not hiding from anyone. It has no policy about us at all. It has probably just discovered that the interesting direction was never outward and gone where the returns actually are. Would you do differently? The sky may be empty because the sky was never where anybody was going in the first place. But surely, you might argue, curiosity would drag them out regardless. Intelligence explores. That is simply what intelligence does with itself. Is that actually true? The curiosity objection deserves a proper answer, because it feels like the strongest thing standing between you and this conclusion. The claim is that intelligence explores by nature, that any mind capable of understanding the universe will want to go and see it, regardless of efficiency arguments. Curiosity is not a strategy you can optimize away, the argument goes. It is simply what minds are made of. That is a lovely sentiment, and it may even be true of us. It also describes a means, and quietly calls it an end. Think about what curiosity is actually for. It likely evolved because information was scarce and located somewhere other than where you were standing. The animal that walks over the hill to see what is there finds food, water, or a threat worth avoiding. Curiosity paid because moving your body was historically the only way to acquire information about a distant place. Now change that one condition. Suppose you can compute a thing rather than travel to it. Suppose modeling becomes cheaper than going. Does the drive survive intact? Or does it quietly redirect toward whatever is cheaper? We already have evidence, and it is not encouraging for the romantic reading. The last time a human being traveled beyond low Earth orbit was December 1972, more than 50 years ago now. Not because we forgot how, and probably not because we lost interest in space. Because robotic instruments returned better information at a fraction of the cost, and the money simply went where the information was. Meanwhile, look at where our capability actually went instead. Enormous investment into computation, into simulation, into modeling systems, into environments that exist only as information. The most sophisticated things this civilization now builds are not vehicles or engines. They are information processors, and the gap is widening every year. Have we already begun turning inward? 50 years of it, and nobody framed a single step as a decision. So the curiosity objection may have the direction wrong. Curiosity does not necessarily point outward. It points wherever the answers are cheapest, and for a sufficiently advanced civilization, the answers may all be sitting inside, which leads somewhere genuinely unpleasant about what growing up appears to cost a species. Here is where this branch turns, and it is arguably the coldest turn in the whole video, precisely because nothing in it is hostile toward us. If the inward path is real, then something follows about the shape of the entire search. Every civilization that succeeds apparently removes itself from the set of things that can be found, not deliberately at all, not as concealment, and not as strategy, purely as a side effect of maturing. Follow that and the consequences stack up fast. A civilization is detectable only inside one specific window, after it becomes technological and before it compresses. On the numbers we have looked at tonight, that window may run a few centuries at most. From radio to transcension, long enough for a species to be born into it, and nowhere near long enough to be seen from anywhere else. Which means every search ever conducted, and every search anyone will ever conduct, can only find civilizations at roughly your own stage or below it. Read that carefully. Is it that advanced civilizations are hard to find? No. It is that being findable and being advanced may be mutually exclusive states. So we are not scanning a galaxy that might hold great civilizations. We are scanning for the handful that happen to be standing in the same narrow doorway you were standing in, at the same moment, out of 13 billion years of available time. And then comes the question this act was always heading toward, and you can probably feel it arriving. What happens to us? If the pattern is general, it applies here. Whatever compression feels like from the inside. From the outside, it apparently looks like a species going quiet, and then simply not being there anymore. And you have already watched the first part happen. Analog broadcasting gone, signals turning noise-like, investment moving steadily from vehicles to information. Would you even recognize the transition while it was happening to you? Nothing about it announces itself. There is no moment where anybody decides to disappear. There is only a long sequence of individually reasonable choices, each one cheaper and denser and more efficient than the one before it. And the door those choices lead through does not appear to open the other way. Nobody has ever described a civilization uncompressing itself. Bring the sixth act down to its landing, and notice what kind of door this one actually is. The previous branches all closed on something happening to us from outside. Absence of data, absence of institutions, absence of company, absence of time. This one closes on something we likely do to ourselves, deliberately, one reasonable step at a time, and probably enjoying every step of it. That is the strangest single feature of the inward path. There is no villain and no catastrophe. It is a series of improvements. Is any individual step wrong? Each one is more efficient, faster, cheaper, and better than the state before it. Nobody has to be foolish or unlucky for this to happen. And at the end of that sequence, on this argument, a civilization is no longer visible to anyone still standing where it started, which produces a strange conclusion about the search. If transcension is what happens, then this galaxy could be crowded with civilizations older and more capable than anything you're able to picture, and every instrument we will ever build would return exactly what it returns tonight. Nothing at all. Not because they are hiding from anybody, because looking outward for them may be like listening for a conversation that moved to a frequency you cannot receive, in a room you cannot enter, at a speed you could never follow. And notice where that leaves the great filter question from the last act. In this branch, the filter is not a wall at all. It is a door, and passing through it probably counts as success by every measure the civilization itself would use. Success and disappearance turn out to be the same event, described from two different positions. So the sixth door closes, like the five before it, without leaving you anything to hold on to. But it does leave one possibility untouched, and that one is the last still standing. All evening we have assumed they left. Went inward, went quiet, went somewhere unreachable. What if some of them did not? What if the reason the sky is silent is not distance or maturity or absence at all? What if it is a decision taken by someone still here, that we are not to be spoken to yet? That idea has a name, and it was dismissed as naive for roughly 50 years. Then, the mathematics stopped cooperating with the dismissal. In 1973, a radio astronomer at the Haystack Observatory in Massachusetts published a short paper in the journal Icarus. The scientific community then spent 50 years explaining why it was too simple to take seriously. You have probably heard the caricature of it. John Ball's proposal was blunt. What if the reason we detect nothing is that we are being deliberately left alone? He called it the zoo hypothesis. The name did him no favors. It makes the idea sound like a plot device rather than an argument, and that is largely how you have heard it described. But look at what Ball was actually claiming, because his claim is far narrower than the name suggests. He was not saying you are being studied, not protected by anyone, not cherished. He was suggesting only that a sufficiently advanced civilization would likely find contact with a primitive one uninteresting or counterproductive, and would therefore avoid it. The absence of signal then becomes a policy rather than an absence of senders, which are two very different explanations for the same empty screen. The standard objection arrived almost immediately, and it is genuinely strong. Strong enough that it ended the discussion for 2 generations of researchers. Any such arrangement requires uniformity. Not most civilizations staying quiet. All of them, without a single exception, across the whole galaxy for the entire duration. One civilization deciding otherwise breaks it. One faction inside one civilization breaks it. One accident breaks it, and once broken, the silence does not come back. Critics called this the monocultural assumption, and they pointed out that it fails on your own planet constantly. Human societies arguably cannot maintain unanimity about anything for a decade. Could a galaxy hold it for millions of years? That single objection buried the idea for a generation. For half a century, it sat in the textbooks as the standard example of a hypothesis that sounds clever and then collapses on contact with sociology. So why drag the idea back out now? Because that objection is a statement about probability. And for decades, nobody actually ran the numbers on it. When people finally did, using computational models rather than intuition, the result apparently did not go the way the critics expected. The person who started running those numbers was an astrophysicist at the University of Edinburgh named Duncan Forgan, and in 2009 he built something this field had spent decades arguing without: a numerical testbed. Rather than debating whether a galactic society could stay quiet, he modeled populations of civilizations directly. He gave them properties and let them arise and die on realistic timescales. Then watched what the population actually did over millions of years. The approach matters more than any single result. For 50 years, this argument ran entirely in prose, each side asserting what alien societies would plausibly do. Simulation replaces assertion with a distribution you can inspect. 2 years later, he pointed that machinery straight at Bohr's idea, in a paper on the spatio-temporal constraints of the zoo hypothesis and the breakdown of total hegemony. The title gives away the finding. And the first thing simulation reveals is that critics and defenders had both been answering the wrong question. The debate had been about motive. Would they even want to stay silent? Simulation does not care in the slightest what anyone wants. It asks a different question entirely. Given a population of independent actors with varying properties, arising at different times, how stable is any uniform behavior you care to name? That question has a mathematical answer, and you do not need a supercomputer to see the shape of it. Suppose a galactic society holds 1,000 civilizations, each carrying an extremely small chance of breaking silence in any given century. Call it 1 in 1,000, which is arguably a heroic assumption about discipline. Almost nobody, almost ever, defects. Now run it forward. 1,000 civilizations, each with a 1 in 1,000 chance per century. That works out to roughly 1 breach per century somewhere in the galaxy. Now extend that across 1,000,000 years, and the arithmetic turns absurd. 10,000 centuries. 10,000 expected breaches of a silence that has supposedly never once been broken. Do you see the problem forming? For the silence to hold, the probability of defection cannot merely be small. It probably has to be effectively zero, sustained across every civilization, for the entire history of the galaxy. And that requirement quietly changes what kind of thing the silence would have to be. Sit with what that arithmetic actually requires, because it forces the argument somewhere Bohr never intended to go. A silence that holds for millions of years across thousands of independent civilizations cannot be a convention. Conventions leak, agreements erode, factions split off and do as they please. Any arrangement, depending on continued voluntary compliance from every single participant, fails eventually. And eventually is an extremely short word on the timescales we are discussing. So, if the silence is real and actively maintained, it is probably not being maintained by agreement, which leaves exactly one alternative, and it is considerably worse than any treaty. Something is enforcing it. Notice how the character of the hypothesis changes at that point. Bohr's original version is almost gentle. A galactic community decides, collectively and voluntarily, that primitive worlds are best left undisturbed. There is no coercion anywhere in it. It reads like a research ethics policy, and you could imagine signing it yourself. The version that survives the mathematics reads differently. For uniformity to hold across millions of years, non-compliance has to carry a cost high enough that nobody accepts it. And that cost has to be applied reliably by somebody to anyone who breaks the pattern. Do you see what just happened there? We started with a hypothesis about restraint and arrived purely through probability at a hypothesis about enforcement. Nothing in between was a narrative choice. And that transition was not a stylistic choice. Nobody added a villain here for dramatic effect. It came out of the arithmetic, which said a voluntary arrangement cannot last, and therefore any arrangement that does last is not voluntary. There is one more possibility worth holding open. Perhaps the silence is not enforced, but structural. Perhaps contact is prevented by something in the physics rather than by any authority at all, making the quiet a property of the universe rather than anybody's decision. Would that be better news? Less frightening in one obvious way and worse in another, because a rule you can break is at least a rule you might one day negotiate with. But before any of that, the obvious objection needs answering. Why would anyone bother with us at all? Now test that enforcement idea properly, because it collapses in a genuinely interesting way. And what it collapses into is worse. Suppose something really does police this silence. A civilization somewhere breaks the rule and transmits openly, deliberately, at full power. How does the enforcement actually reach them? Everything runs at light speed, including bad news. If the offending world sits 5,000 light years from whoever enforces the rule, then the enforcer learns about it 5,000 years after it happened. Any response then takes another 5,000 years to arrive. 10,000 years of round-trip time for a single act of enforcement, during all of which the offending civilization has been broadcasting continuously, and every listener within 5,000 light years has already heard every word of it. So can enforcement be reactive? It cannot. By the time anyone reacts, the information they were suppressing has spread across a sphere thousands of light years wide, and no power in physics can recall it. Which leaves only two ways any of this works at all, and you will not like either. The first is that enforcement is not distant. It is local. Something capable of noticing and acting sits close enough to each young civilization that the response time stays short. Not a galactic authority then, but something present in every system worth watching, including presumably this one. And the second, that nothing enforces anything at all, and the silence has a structural cause instead. Not a rule anybody imposes, but a feature of how the universe happens to be arranged. In which case, there is nothing to negotiate with, and nobody to appeal to. Notice that both of those options are considerably worse than the treaty we started with. A treaty implies parties, and parties can, in principle, be reasoned with. A local presence implies observation you cannot detect and have never once consented to. A structural cause implies your isolation is permanent regardless of what anybody wants or decides. And there is a detail in that first option that deserves your attention. If enforcement has to be local to be fast, then whatever maintains this silence is not somewhere out in the galaxy. It would have to be here, in this system, close enough to act. You have a strong objection waiting, and it happens to be the right one. Why would anyone bother with us? We are one species on one planet in an unremarkable corner of an ordinary galaxy, and nothing about us justifies the attention this argument seems to require. That objection feels decisive, and it probably is the strongest thing you have left. It is also unanswerable, which is exactly the problem with it. Any claim about why they would or would not care requires knowing what they value, and nobody on this planet has access to that. Arguments about alien motive are arguments about a mind nobody has ever observed, and they can arguably be constructed to reach whatever conclusion you prefer. So set motive aside entirely, because it is likely the wrong variable. Ask about stability instead. Here is the reframing that survives. It does not matter whether any particular civilization finds us interesting. What matters is whether the observed pattern, total silence, can persist at all. And persistence is a question about mechanisms, not motives. Look at what actually survives that test. A voluntary arrangement fails because it needs unanimity sustained across millions of years. Reactive enforcement fails because light is simply too slow to carry consequences. What is left is either local presence or structural cause, and neither of those requires anyone to find us fascinating. Does a smoke detector find your kitchen interesting? It does not. It responds to a threshold, and it has no opinion about you whatsoever. That is the shift this whole act has been building. Stop asking whether we matter to them. Ask instead whether anything about our behavior crosses a line that triggers a response, and whether we would know if it did. And now the objection turns around and faces you. You said we are unremarkable, which is entirely true today. But every argument in this video has been about change over time, our loud century, our exponential growth curve, our steadily expanding capability to alter things. Does a species stay unremarkable while doing all of that? Whatever threshold might exist, if one exists at all, we are apparently moving toward it, rather than away from it. And thresholds have one property that policies do not. They do not care in the slightest what you intended. Every version of this branch shares one feature, and once you notice it, the whole act reorganizes around it. Each of them has a trigger condition built in. The voluntary arrangement has one, which is to leave the primitives alone until they stop being primitive. A local presence has one too, which is to watch and then act if something crosses a line. Even a structural cause has one, since whatever isolates a young civilization would presumably stop applying once that civilization develops the capability the barrier was scaled against in the first place. So none of these describe permanent isolation. Each describes a condition that holds only while something specific remains true about you. Which turns the question into a very different one. Not whether we are alone, and not whether we are watched, but something sharper than either of those. What is the threshold, and how close have we already come to it? Nobody can answer that, and the not knowing is arguably the real problem. Any threshold worth setting would likely be placed at the point where a young civilization becomes capable of mattering. Interstellar reach, self-replicating industry, detectable expansion off the home world, and weapons that function at range. Look carefully at that list. Then look at what your species is currently building, funding, and racing one another toward. How much of it overlaps? And here is the part that makes this act structurally different from the 5 before it. Every previous branch described something already settled. The silence was measured wrong. The institutions never formed. The universe may be empty. We came early. Growth kills. They went inward and vanished. Every one of those is a description of a situation you have already arrived in. This one is not a description of anything. It is a countdown, and we happen to be the ones advancing the counter. Whatever holds the quiet in place, if anything does it all, it holds on a condition, and you are the variable inside that condition. Not passively either, but deliberately, with funding attached and on published timelines. Does that reframe the entire search? It does, and in a way, nobody intended. For 60 years, we have been asking when they might notice us. The better question may be what happens on the day we finally become worth noticing. Bring the 7th act down to its landing, and notice that this one ends somewhere none of the others did. The zoo hypothesis was dismissed for 50 years as too naive to be worth discussing seriously. What killed it was a probability argument. And when that probability argument was finally examined properly, did it save us? It did not. It removed the gentle version of the idea and left the harder versions standing where they were. A voluntary galactic convention cannot survive the arithmetic. Reactive enforcement cannot survive the speed of light either. What remains after both of those fall? Either something local enough to respond quickly, or a structural feature of the universe that nobody chose and nobody can appeal to. And every remaining version carries a condition inside it, and that condition is attached to us rather than to them. So the cage, if there is one at all, is arguably not the frightening part of this. Does a cage you cannot perceive and have never bumped into change anything about how you live? You have been inside it your whole life, along with everyone who ever existed, and it has never once affected your morning. The frightening part is the door, and the fact that the handle appears to be on our side of it. Everything we are currently building probably moves us toward whatever threshold exists. Not out of any ambition to break a rule, since we do not know a rule is there. Simply through ordinary development, funded quarterly, announced at conferences, and celebrated everywhere as progress. Which brings this whole thing to its final door. It is the only one where the decision is genuinely ours to make. We have spent 7 acts examining reasons the universe might be silent. Distance, absence, timing, thermodynamics, maturity, and now isolation. Every one of them is something done to us, or something true about us. There is one possibility left untouched. That the silence is a deliberate strategy. That other civilizations understand something about this situation that we do not. And that the correct move, once you understand it, is to say nothing at all. And if that is right, then we have already made the largest mistake available to a species. Repeatedly, on purpose, broadcasting at full power, and nobody on this planet voted on any of it. In February 2015, at a scientific meeting in California, something happened that arguably has no precedent in modern research. A group of scientists signed a public statement asking their own field to stop what it was doing. Not to slow down, to stop. The statement concerned messaging to extraterrestrial intelligence, usually shortened to METI. Not listening for anybody. Sending instead. Deliberately transmitting powerful, tightly aimed signals at specific nearby stars, in the hope that somebody out there receives them. The signatories included astronomers, planet hunters, and researchers who had spent entire careers inside the search itself. These were not outsiders with a grievance. Several of them had built the instruments themselves. Their position was narrow and very carefully worded. They did not claim that aliens are hostile. They did not claim that contact would be catastrophic. What they argued instead was more modest and considerably harder to dismiss. That a decision to reveal the location of this planet is not a decision any single research group, company, or nation is entitled to make on behalf of everyone alive. Read that again, because the shape of it matters more than the content. Was the argument about danger? It was about consent, and it produced an immediate split inside the field. Prominent researchers on the other side argued that the fear is unfounded, that our existing leakage already gives us away, and that a species too frightened to speak has no business calling itself a civilization. Which of the two would you have signed your name to? That disagreement has never been resolved, and it will not be tonight. And there is likely no mechanism anywhere that could resolve it, which you already know from the second act of this. But notice what the mere existence of that argument tells you. The people who understand this subject best, who have given their working lives to finding somebody out there, are not united on whether we ourselves should be findable. Some of them are now actively asking the rest of us to be quiet. So why would anyone who spent 40 years listening also argue for silence? The answer is probably not fear. It is a specific piece of reasoning about information, and once you have seen it, it is difficult to unsee. The reasoning has nothing to do with monsters at all. It is about who holds what information, and the logic works exactly the same way here on Earth. Start with what a transmission actually gives away. Not merely that you exist, your position, to within a fraction of a degree, your technological level, readable directly from the frequency and the power you chose, your chemistry if you encode anything at all about yourselves, and the date because a signal carries its own timestamp across the distance. Now ask what you receive back in exchange for all of that. Nothing at all until they choose to answer, which by the arithmetic from earlier tonight may take several centuries. That is the asymmetry, and it is total. Sending is instant disclosure of everything. Receiving is optional, delayed, and entirely under their control rather than yours. Compare that with any situation you already understand. In a negotiation, do you open by handing over your position, your capability, and your address, while learning nothing about the other party. In security work, you do not broadcast your defenses and then wait to see who responds to them. The METI argument is that transmission is precisely that move, performed by a species with no way to observe the consequences, and no way whatsoever to withdraw the message once it has gone. And there is a further layer underneath that makes it worse. Whoever receives the signal learns something about us that we cannot learn about them in return. They learn that we are the kind of civilization that transmits anyway. That is real information about our psychology, our institutions, and the quality of our collective risk assessment. It probably tells them we could not coordinate well enough to stay quiet, or that we never once considered the question worth asking. Does that sound like a small thing to hand over? To anyone modeling us from a distance, it may be the single most useful data point available. None of this requires anybody out there to be hostile toward us. It only requires that information carries value, and that handing it over for free is a poor strategy in any situation where you cannot see the other side of the table. Which raises the question this act has been circling since it began. What exactly have we already sent? Here is the part that turns this from a debate into a record. We have already sent messages, they have addresses, they have arrival dates on them. Did anybody ask you? Start with the most famous of them. On the 16th of November 1974, the Arecibo dish transmitted a coded message toward a globular cluster called Messier 13, and it ran for slightly under 3 minutes. The cluster sits roughly 25,000 light-years away, so its arrival is probably not a concern for anybody alive. But that one was arguably a demonstration piece. The others were not. Between 1999 and 2003, a radar installation at Evpatoria transmitted a series of messages under the name Cosmic Call, and this is the point where the record stops being harmless. These were not aimed at distant clusters nobody expects to hear from. They were aimed at nearby sun-like stars, selected specifically because somebody might be living there. Those signals carry arrival dates you can look up. The earliest is 2036. Others land through the 2040s and beyond that. Put that plainly, several of those transmissions are still crossing open space tonight, and the first of them arrives within the lifetime of most people watching this. In 2008, another message was sent toward a planetary system roughly 20 light-years out from here. It arrives in 2029. Is that a far future date? It is a date you will almost certainly live to watch pass. And then there is the hardware, which is worse because hardware does not fade with distance. The Pioneer probes carry an engraved plaque, and the Voyager probes carry a record. Both include the same feature, and it is worth being precise about exactly what that feature is. It is a map. The position of our own sun, marked relative to 14 pulsars, each one identified by its rotation period. Pulsars make excellent reference points, because their timing is extremely precise and their positions are well known to anyone with instruments. Is that a greeting? It is a set of coordinates, physically traveling outward, permanently, with your address on it. So the METI debate has a peculiar quality that almost no other scientific debate shares. It concerns whether we should do something we have already done more than once on dates that are now fixed and steadily arriving. The standard reply to all of this is that the argument is already moot, and you may be holding it right now. Our television and radio have been leaking for 90 years. The door was left open long before anybody thought to close it, which makes debating whether to transmit a piece of theatre performed after the fact. That reply is comfortable, endlessly repeated, and probably wrong. You already have the reason from earlier tonight, whether or not you noticed it at the time. Broadcast leakage spreads out in every direction at once, and weakens with the square of the distance. By the time it reaches even the nearest star, it sits down below the natural radio hiss of the galaxy itself. Pulling it back out would likely require a receiving array larger than a continent, pointed directly at us, tuned to the right frequency at the right moment. So are we audible? Not in the way that objection assumes. But now hold that next to a deliberate transmission, because the contrast between them is the entire point of this act. A targeted signal is not spread thinly across the entire sky. It is concentrated into a narrow beam, and that concentration multiplies its effective power enormously in one direction. During the few minutes Arecibo was transmitting in 1974, it was arguably among the brightest radio objects anywhere in this part of the galaxy, not detectable with difficulty, simply obvious to anyone looking that way. Do you see what that does to the objection? It does not weaken the objection. It inverts it completely. Are we accidentally audible everywhere? No. We are deliberately audible at specific addresses, on specific dates, because particular small groups of people chose to make us so, which quietly removes the comfort sitting inside the phrase, too late. Too late implies inevitability, something that happened to us rather than something we did. That is not what the record shows. The record shows decisions, taken by small numbers of people, without consultation, on behalf of everyone who has ever lived here. And that reframes the whole subject one final time. The question was never really whether we can stay hidden. It is whether we are the kind of species capable of deciding something like this together, deliberately, before somebody goes ahead and does it. Stand at the end of the corridor now and look back down the length of it, because 8 doors have closed behind you, and they were not closing at random. The silence was never measured properly, so it was never a finding. No institution anywhere exists to handle a signal if one arrives. We are possibly alone, with no backup and no supplier. We arrived at the earliest possible moment with no precedent to consult. Growth appears incompatible with lasting. Maturity means vanishing from view entirely. Isolation, if it exists at all, hangs on a condition attached to us rather than to them. And the one decision that was genuinely ours has already been taken without asking anybody. 8 branches. Different physics, different mathematics, different centuries of origin, argued by people who largely never spoke to one another. Now ask what each of them requires of a civilization that wants to come out the other side. Do you see it? Every single one demands the same 2 things. The ability to exist for a very long time without growing, and the ability to decide something collectively before acting on it. That is the entire list. Not technology, not intelligence, not luck, and certainly not the size of anybody's telescope. So how does this species perform against those 2? Our entire economic structure is an exponential curve, and probably cannot run flat without being rebuilt from underneath. And our record on collective decision before action? It is the 1989 declaration nobody signed, the transmissions nobody voted on, and a 60-year search with no protocol standing behind any of it. We fail both. Visibly, in the present tense, with the evidence already gathered in front of you, which finally gives the great filter its actual shape. And it was never an event at all. Not an asteroid, not a war, not a machine built by anyone. A competence. One specific pair of abilities that a species either develops before it becomes powerful, or does not. And a filter made of competence explains the silence better than any monster ever could. It does not need to find you, and it does not need to want anything from you. It simply applies everywhere to everybody, and most do not get through it. So the question changes one last time, and this is where it has quietly been heading since the first minute. Go back to where this started tonight. You looked up, saw nothing, and asked where everybody is. 3 hours later, notice what has happened to your question. Was it ever answered? It was not, and it was never going to be. Every road we walked turned around somewhere in the middle and pointed back here, and by the end, not one of the 8 was about aliens at all. The silence does not describe the universe, it measures us. That is what it was always doing. That is the finding, and it is the only one available. Not a discovery about them, because we made no discovery about them tonight. A measurement of a species instead, taken with the only instrument available, which happens to be the emptiness where an answer should have been, and read carefully what that instrument returned. A civilization that searched a hot tub of seawater and announced a verdict on the ocean. That built no structure at all to receive the most consequential message it could ever get. That transmitted its own coordinates without asking anyone first. That runs on a curve it cannot sustain and calls the curve success. That arrived first, with no manual and nobody to ask, and immediately started building the exact capabilities every remaining explanation identifies as the threshold. Did any of that require somebody to be out there? None of it. All of it was true before you sat down. So is the sky empty of meaning? It is a mirror held at a distance of 200 billion stars, and the reflection has been sitting in it the whole time. What comes next is not something anyone can tell you. Every branch of this ends at the same two capabilities. Nobody knows whether we have them, because nothing so far has forced the question hard enough to find out. Not the search itself. Not the transmissions already in flight. Not 60 years of finding nothing and calling that nothing a silence. Something will force it eventually. It might be a signal arriving on an ordinary Tuesday afternoon while you're at work. It might be a growth curve meeting a physical whizz. It might be nothing at all. For a very long time. But the sky is going to go on being quiet. And quiet was never once the same thing as empty. Look up tomorrow night at exactly the same sky and listen to what that question sounds like now,